I'd like to share some of the new modules that we've created with MathWorks for teaching chemical engineering with MATLAB, Simulink, and TCLab. My name is John Hedengren, and I'm an associate professor at Brigham Young University. Over this past year, I've been able to work with the MathWorks team and Joshua Hammond, who's a research assistant in the PRISM lab, to develop some of these modules and really transform how we teach to make interactive, immersive experiences for students. Let me share with you some of the interest that we received over the past week. So I posted this just a little under 7 days ago about these 35 new interactive modules, and posted the webinar registration, a link to the modules, and then this flowchart about how we teach process control. As you can see, there was a large response and many encouraging comments with individuals from universities, from industry, and around the world. So thank you for that interest, and thank you for all of the encouraging comments about this initiative. I want to give an overview today about why automation is needed across industries. And as we look at Industry 4.0 and how many industries are being transformed by data, by algorithms, and computing power, we see a need for individuals to be trained on these topics. And so we wanted to create these 35 lesson modules that give a very interactive experience for students who are learning process dynamics and control for the first time. Also introduce this pocket-sized lab, the TCLab, with teaching resources for learning objectives, where you can take some of these modules and drop them into your existing course, or if you're self-studying, you can work through these at your own pace. And then also share some other additional collaborative community resources. So as we look at the automation impact across industries, we think about industries like medical automation, where a surgery may be done by a robot with more precision and control, or with semi-closed loop, where you have perhaps a physician that's able to use one of these as a physician's hands to get more precision during the operation. We also look at people and product transportation and how those are changing dramatically in terms of self-driving cars or ways that we move products from the producers to the consumers. We also look at traditional industries like the oil and gas industry, and those are also being transformed by new topics in data science, analytics, machine learning, cybersecurity, and digitalization. So the pace of this is happening very fast, and there are many opportunities for students in these areas to be part of this transformation. So with that in mind, we've developed these dynamics and control modules. There are 35 of them, and through each of them we take 3 steps. The first one is theory, where we teach the background and fundamental knowledge that the students need to be able to understand what are the fundamental factors and the equations and the derivations. And then the next one, we have a simulation where it's an assignment where they work on it themselves. There's no hardware involved, but it's these interactive modules where you can slide things back and forth and see an effect, or be able to change something, see a cause and effect relationship, start to develop some intuition for this. And then we also have a lab with each one. So theory, simulation, and lab. And with this, it's the temperature control lab. And I'll be introducing this a little bit more. But if you'd like to go to these, let me just bring you to this. And if you bring up a web browser and type that in, you'll come to the course website. And if you select course schedule, it will go to this outline of here's the theory, here's the simulation, and then there is the lab activity. And along the way, there are also quizzes For example, which of these is not a conserved quantity for a basis for a balance equation? And so students can come here and say, well, it's force, that is correct, and it gives some explanation on why that's correct. So for example, momentum is a conserved quantity, that's incorrect. So it's these low stakes quizzes that students can take to test their understanding after they review the theory. And then there's the simulation assignment and then the TCLab activity. Now these are both available in Python and MATLAB, so if you select the MATLAB, that will bring you to the archive with these MLX extensions that you can download with download zip file, or you can grab the repository with this clone command. Okay, so each of these have these three areas: the simulation, the theory, the simulation, and then the lab for each of these. And so first of all, I just wanted to show you where you can get those if you'd like to grab those and then mix them in with your instruction if you're a university professor, or if you are a self-studying student, you can go through at your own pace. All right, let's talk a little bit about learning from the instructor perspective. So instructors traditionally in the past have had lab experiments that perhaps were at a university or part of a unit operations lab where students could come in and use those. And there's many students in the class that would need to schedule time to use that experiment. And each of those took time. You could do it sequentially, but often there's limited time for each student to work with the lab. And so the teacher would teach an assignment, and this new way of doing it is to give a lab to each student that they then take home, or they work on in class as part of an in-class activity. And so it's different than this single lab where the lab is given to each individual student and they have an experience with the lab that's not just for a limited amount of time, but can be throughout the semester. Let's think about the student themselves. And so that was kind of from the instructor perspective, difficulties in scheduling the lab time, managing students and their learning experience. But let's think about it from that individual student. And when you're first learning a topic, there are foundational items that you really need as a student to be able to feel comfortable building upon those and getting into more advanced topics. One of the things that I've seen with students is that there's often a the intimidation that comes from even programming. Okay, so one of the things that we did is put together these 12 modules just to be able to begin MATLAB. And MathWorks also has a very nice on-ramp, many modules there to help somebody who's learning MATLAB for the first time. We also put these 12 together, in particular with the TCLab. And then students go from the theory to the simulation to the exercise, and they're going to do this repeatedly in this loop until they gain this foundational knowledge. Okay, so this is like if you took a travel and went to the airport. This would be the takeoff phase where you're starting to gather speed. You're very dependent on solution keys, on this foundational, and then finally you start to take off and start to gain wings and start to gain elevation in understanding. All right, and so we take students through this journey, and through each step of the way, we start with, we take them through this entire journey together and build these foundations and get higher and higher in terms of their understanding. And they gain somewhat of a perspective as they go along as well. Okay, and so this perspective, as they're going along, we want to point out landmarks to them. So for example, throughout their journey, There might be things like different models that they can create. All right, and then these feed into, is there a measured disturbance? If yes, then we design a feed forward or cascade control if we want to be able to reduce the disturbances. If not, then we evaluate if it's an integrating system. If it is, then we use a P-only control. If not, then we can use a PI or PID controller. Then what we do in this course is we then analyze stability limits to say, okay, we have selected one of these. What are the limits of our gain that keep us stable? And then we use tuning correlations. So for example, ITAE or IMC, or there are many other types of tuning correlations, ways to get from perhaps our first order plus dead time model into something that is KP, KI, KD, or KC tau I, tau D, which are functionally equivalent, and come up with the PID controller tuning values. And then we go into a phase of evaluating the controller performance, and if it's unacceptable, then we tune the controller. All right, and then come back and then decide if it's acceptable, and then we monitor PID performance. So this is just one example of this roadmap that we build for students, and then there are these modules for each block along the way. So I'll show you some of these, how to, for example, create a first order plus dead time model and make that very interactive and immersive for students. Okay, so this is the TCLab, and here we have the heater values right here, and then also the temperature. And this is what we want to get to here, where here's our set point. All right, and then we have the measured PV. So this is actually coming from the device. This is the temperature right here, and there is our heater value. Okay, so the heater is right here, and the temperature sensor is right here. This is just one of the two of them, but this is what we eventually want the students to get to. But they need some background information. We first of all review things like controller design, these fundamental concepts of things like controller output, a PV, a set point, and then some of the energy balance equations, linearization, and others. So as we develop these fundamental or first principles models, and then also empirical models on top of those. Okay, and so the other challenge with labs is making them very easy to use. And so with this lab in particular, we wanted to be able to take a computer and have this be plug and play. So they plug it as a USB into their computer, and then also hook up a power source for the heaters. Okay, so the heaters need some additional power that the computer can't provide through the USB. And then we are able to control those through MATLAB. So we first of all just load the lab. We can do things like turn on the LED to 80%. We can display temperature 1, and we can adjust the heater 1 to 50%. Okay, so those are some simple commands that students can use. I'll also show how to do this in Simulink as well. If you have two heaters and two temperature sensors that you want to control, okay, so here we have heater number 2 and heater number 1, and they're next to each other. They feel some of the effects of the heat from each other, and it's very easy to also display those other temperatures and control both heaters. And this is an example that we'll show later about model predictive control with two controller outputs and 2 set points. All right, so let's just start from the beginning. The very first thing that students do in this sequence is do some step tests on their system. So they have the heater value. They can step up and down, and they want to be able to see the temperature response and compare that between simulation, the equations that they've developed, and what actually happens in practice. And one of the most informative things is when there's a difference between the two. They start thinking about their equations and what am I missing in terms of my concepts until they align better. All right, so I just want to show you how to do this in Simulink. You can start from scratch and build up from the raw signals that come from the Arduino. And then there are some sliders here that they can adjust. So they're turning those raw signals into temperatures, those voltages into temperatures, and then when they select go here, then you can see the temperature outputs. Okay, so that's the very first thing. We've built the Simulink module. And now what we can do is we can take those and we can adjust with the sliders. Okay, and you're going to see this come up. Okay, I set it to 53% here, and you'll start to see temperature number 1 increase. All right, so temperature number 2 is going to remain relatively flat. Okay, it's going to feel some of the effect of the heater, so it might come up a little bit, but you can see temperature 1 that's increasing much more as it goes up. You can even see some things like data noise, which is very valuable for students to understand that not everything is perfect in terms of measurements. Okay, so here you can see just some step tests that students can do. They can wait till it levels off and then calculate things like a gain and a time constant. Okay, so how fast it gets there, and also things like dead time. So that's the very first thing that we can do. And then we could also do first order plus dead time graphical, or also regression fits. So this is an example of one of the live scripts. You can view the lecture, so there's a solution video with each. And so as they take it into the live script, you can see that this FOPDT, this blue line right here, is going to adjust as they move the slider bar back and forth for the gain, the time constant, and the dead time. Okay, so it gives them somewhat of an intuitive understanding as they work with these interactive modules, what each of these factors do and how they influence the way that you can fit a first order plus dead time model to some data. All right, so students go through this and they gain an intuitive understanding with these interactive modules, and then the next step is then to take this to a PID controller. So we're going to be focusing on this one right here, tuning a PID controller. I'm just showing a sample of some of these. There are the 35 different modules. But then students come in, and in simulation they can now adjust these 3 parameters here, KC, tau I, and tau D, which are the P, I, and D factors. And you see as you adjust those back and forth, you can see this plot, the simulation plot, changing here on the right. And then after we do this, we're going to then apply it to the TCLab and let students generate their own data to see how well the factors perform on the real device. All right, so along the way you'll also see these view solution checkboxes that help students if they need help with the solution if they get stuck. Okay, and there's also a solution video for each one. Here I've gone to 12 times the speed, and you can see the PID controller performance as it automatically adjusts the heater in order to try to meet the set point. Okay, so this is an example of our live script and how it works. I really like these interactive live scripts. Give students, we've taken away some of the coding burden of the exercises to allow students to really focus on the concepts. Okay, and then we can also have them build a PID controller directly in Simulink. So this is an example of aligning with some of the things maybe in a textbook where you see a standard block diagram, and I'm going to line up the set point and the PV. I'll put a PID controller in there. I'll drop that in from the library and then put a summation in as well. Just adjust the sign so you have a plus and minus, and then I'll right click and bring that signal back to complete my control loop. Okay, and then I just want to be able to view this in the scope to be able to see the controller output, the PV, and the set point. All right, and adjust the tuning parameters, the proportional, integral, and derivative. I'll limit the output between 0 and 100, and then use anti-windup. All right, so here's my standard PID control block. The thing in the middle is the actual hardware, so it's going to generate some data for us, and we can have them either use the live script where it's done for them, or we can run through this where you can see the PV right here. Here's the set point. That's our target value, and then as students go along they can even adjust the PID control. So you see here, that was when we made the controller more aggressive. We increased the controller gain, and so they can adjust it as they go along. There are many other things you can do with this as well. I just want to give an overview of some of these. It goes later on in the class. We do introduce things like model predictive control, but there's a complete other course available on this with many interactive modules. Let me just show those to you. APMonitor.com/DO for the dynamic optimization course. And then if you come down here to Arduino Lab. All right, here's Arduino Lab, and this has many more lab exercises, lab A through H, more on the advanced control side. Okay, so if you're interested in that or teach an advanced control class, those modules are available both in MATLAB and Simulink. And so let me introduce just a couple more of those. So in this case we have two set points, maybe a dead band that you want to try to control within this range, and so students develop this themselves and then work with real data. Also we work with this moving horizon estimation and model predictive control, where you can see some of the parameters that are being estimated as you go. So we're using this part here on the left. That's our estimating, okay, estimating our parameters. And then the part on the right is our predictive controller. Okay, so we use those to look forward into the future and be able to make control moves along the way. All right, there are also other modules as well, some data science modules that are in English, and then they've recently also been translated into Spanish with Spanish videos as well. And then we also use this TCLab as well in the machine learning class. So there's a machine learning for engineers class. I'll just show you this one as well. Okay, so again, I'll probably give another webinar on this as well, just what we use with machine learning. And if you go to the schedule, you'll see that this one also uses a TCLab to help teach machine learning and data science. Okay, so this is one example of that. Let me just share this with you. We have the temperature of the TCLab, and we have the derivatives as well. Those are some of the features that we've developed. And then we're going to use some of these supervised learning methods, logistic regression, all the way down to neural network. Those are all supervised learning methods. And then k-means clustering, Gaussian mixture models, spectral clustering, which are unsupervised learning. So you haven't given the labels to those on whether the heater is on or off. Okay, so that's our label. Heater is on or off. So let me just show this in action. So we're using machine learning to do equipment monitoring to be able to see if there's a problem with the heater. So if we tell the heater to turn on, but it isn't really on, that's where this machine learning is going to be able to monitor. And so we've trained in this first part, and then you can see the performance of these different methods as you go. So you can determine if the heater is on or off just by looking at the temperature and the temperature derivatives as well. And then you can see the performance of these different methods. Again, these are the supervised learning methods, and then also the unsupervised learning methods. So many more things that you can do with this TCLab module in terms of teaching process dynamics and control, machine learning, data science, and advanced control. All right, so for instructors, I appreciate the almost 250 people that have logged on to this webinar. For instructors, if you'd like an evaluation version of this, please send me an email with your name, shipping address, and course information. There are some countries where the packages don't arrive, however. So if you know of somebody visiting the U.S. that could take it back to you, I'll be glad to give you some information about alternatives to be able to get one of these. For the U.S., it typically arrives in 2 to 3 business days, and international, there have been more issues with backups in customs, so it's typically 20 business days, so up to a month or so to receive the package, sometimes even longer. And then when you evaluate this, if this is something you'd like to use for your course, you don't necessarily have to order these for your class. You can just give the students this link. It will take them to a place where they can order it themselves and then use it as a resource in the class, much like you'd use a textbook that they also purchase. And so there are options for you to be able to use this, deploy it for your class. We try to keep plenty in stock. Or if you want to get a batch from me as well, that is another possibility. All right, so let me talk about some other resources that are available. There's also this cache teaching resources page, and as we talked about in the title, it's teaching chemical engineering. So the one that I've shared is more on the process control side, and then I also maintain this list on computer programming. So just helping students with learning programming for the first time. But there are many others, such as Introduction to Chemical Engineering, Material and Energy Balances, Fluid Mechanics, Heat Transfer, and many others. So I hope you are able to use this. Also, if there are other resources that you'd like to contribute to these lists, please reach out. And then also I'd like to highlight something from Brian Douglas. He's working on this resorcium.org website, and here you can search for these featured journeys, a collection of resources to help you with things like PID control, Kalman filters, what is systems engineering. You can build somewhat of a roadmap for yourself based on this aggregation of all these resources that are available online. And we're working with Brian on this as part of the IEEE Control Systems Society Technical Committee on Control Education. So I appreciate also your participation in this as well. Feel free to use this resource and give feedback to me or Brian on this new resource that's on the web. I also like to thank many collaborators on this project who have enabled this community resource. started in the early days with Jeff Cantor and Carl Sandrick. Jeff is at Notre Dame, and Carl is at University of Pretoria. And then also later we had Paulo Moura Oliveira and John Anthony Rosatier at University of Sheffield, and Paulo in Portugal, just on developing modules. In the case of Paulo, translating into Portuguese. And then there have been many at BYU who have helped develop these as well. So appreciate, in addition to Joshua Hammond, who led this effort, there have been other BYU students, Abe for developing the TCLab module in the first place, and then others have developed software and other things around this. Also like to thank MathWorks for their support, for Melda, Sambith, and iJohn, on their technical and financial support for some of the students to develop these modules. It wouldn't have been possible without them. Here are some references as well. These are all from 2020 right here, and then 2019. So many educational studies and updates on this TCLab and how it's having an effect in classrooms, and some of the resources that are available. So I have some of those links as well. Those are also listed on the website if you're interested. So with that, I'd like to thank you for your participation, and for the many instructors and others around the world who have adopted some of these and have given feedback. So I really appreciate the feedback on how you teach process control, and we'll hope to hopefully be able to pull together more resources in meaningful ways so that instructors are assisted in teaching these very important topics.